This question asks you to show this relation, this identity, and by using the Fourier series expansion of this function f(x) just x. This, I mean, we worked that out in the example of the textbook also, but we could easily do that again. And now we write like a Fourier series in the period of 2 pi. That is like using the standard form. You have c over 2 plus sum over n of b sub n, or the cosine term, and b sub n, or the sine term, at x. Right. And then this is a period of 2 pi, so x is 0, minus pi over pi in 2 pi. Okay. By using that symmetric domain, then obviously when you calculate all the a sub n will be just 0. Yeah, because that function is a odd function, or the symmetric the symmetric terms, the cosine term, and the constant term will automatically be 0. So these are 0. So you need to just calculate b sub n. Now b sub n is, using the formula, it's 1 over pi minus pi to pi f, and then multiply sine and x dx. Okay, and then this can be done by integration by parts. Right. And you get this one is minus cosine of x minus cosine nx over n. And evaluate that. I mean, you can first, because this is odd, this function is odd, multiplied by x is also odd. So this becomes even function. You can integrate from 0 to pi and multiply by a factor of 2. So this factor of 2. So the limit can be 0 to x, 0 to pi. Okay. And then the other term is plus, you have n here, and integrate from 0 to pi. Now dx, derivative of that is dx, and then cosine and x. Right. And the second term will be 0 because this integrated sine nx, and n is from 1 to infinity, and so evaluate both 0 and pi will give you 0. That part is 0. So so that one is you evaluate that 0 will be 0 because you have an x. Evaluate pi, you have pi is for cosine n pi is minus 1 to the power n, right? Cosine, because n equals 1 will give you a negative 1. So, and combined with the negative sign, you have 2 over, and the evaluate pi cancel with the pi, 2 over n minus 1 to the n plus 1 power. Okay, so these are the these of n. All right, then you can use all the b's of n in the Percival identity. So Percival identity, the left hand side is the f squared and integrate over the domain and divided by pi, and the right hand side is summing over all the coefficients square, so the summing b sub n square. All right, so this implied 1 over pi minus pi to pi. F squared is x squared dx. And then that gives you, again, you can change it as 0 to pi and multiply by a factor of 2 and integrate to x cubed over 3 and only become pi, the cubic power divided by pi square equals to 2 pi square over 3. Okay, so that's the left-hand side of the Percival identity, and the right-hand side is just the square of all these b's of n. Sum of n 1 to infinity, and the square gives you a factor of 4 and 1 over n squared. Okay, so that the summation, and this is, you identify this as one value of the Riemann zeta function, but it doesn't matter. It just, this is basically just a sum, which is a convergent sum, obviously, because 1 over n squared. But the question asks you to show this equals to an alternate series. This is not an alternate series. This is other than the factor of 4. This is like 1 plus 1 4 plus 1 9 plus 1 16 and 1 to given. All right, so this is not that. So this is so you will need to manipulate this a little bit to get to that one. And then there's another method to use the series itself, and get another identity, like integrate term by term. That can be done to show that, but there's another way to get an alternate series from the original series, and it's involved something like a trick, but we actually, there is some discussion in chapter 13 or chapter 12 how to do that. Basically, to identify that, say, this whatever this sum we call the Riemann zeta function at argument 2, and you just realize that this one, you keep all the odd term, so you keep all the odd term will be part of this one. So let's just write out separately. So the Riemann zeta function, this sum over 1 over n squared, is equals to, just write like that. So 1 plus 1 4 plus 1 9 plus 1 16 and so on. Now you want this series, so you write like 1 minus 1 4 plus 1 9 and minus 1 over 16 and plus all that. You want this one, but this change to this by minus 2 of the 2 of this 1 4th plus 116, right? Oh, this is plus, because you want to minus that, so you need to plus 2 of that, and 2 of that minus this give you back to this, right? All right, and then you realize that you can pull off a factor of 2 before you take the square, so 2 become a 2 square. So this one becomes 2 divided by 4 becomes 1/2. Just the second line. Just the second line is 2. Take a factor of 4 become 1/2 of this becomes 1, and this is take a factor of 4. This is 1/4, and so on. And you can convince yourself this is exactly this one. So this is just this one. Okay. And so and this is this plus 1/2 of this one. So you subtract this to the other side, uh, becomes this is the same as this is just 1/2. All right, so this means that this summation, which is what we want, which is this one, is 1/2 of the summation. All right, so so I can say this way that so this one is just this one. I can now write it like sum over n from 1 to infinity minus 1 to the n plus 1 over n squared now equals to this minus that is 1/2 of this sum over 1 over n squared, right? Again, 1 to infinity. And now we already worked that out, this identity. 1 over n squared is 2 pi squared over 4. So this is, so this sum is divided by 1/6, pi squared over 6. This one is pi squared over 6, and then divided by 2 is 1/2 of pi squared. 1/12 over pi squared. Okay, so that is this one. All right, so you can do it that way also.